Hagi, who is Chief Security Officer at Silicon Labs. Sharon oversees the company's cybersecurity strategies and best practices for delivering advanced security technologies as an integral part of Silicon Labs' IoT hardware and software portfolio. Prior to Silicon Labs, Sharon was Vice President of Security at Ethica, a global provider of collaboration-based technology enabling card-issuing financial institutions, e-commerce merchants, and online businesses to tackle fraud, chargebacks, and disputes. Sharon was also Chief Technology Strategist at IBM Security. His presentation is titled Securing the IoT and will detail how security threats have changed and escalated, focusing more than ever on the Internet of Things. In addition, recent regulations are placing more pressure on manufacturers to step up security best practices, such as security specifications for IoT devices. And he will also explain how the latest IoT device security tools are helping to protect devices and data and ensure regulatory compliance. So without further ado, Sharon, over to you.
Thank you, Joe. Well, hello, everyone. We'll just get started right away. So in information security, and in particular, security architecture and design disciplines, we consider a number of principles. And one of these principles says that the overall security of a system is only as good as its weakest point. We call it the weak link principle, alluding to the overall strength of a steel chain. And in fact, that the chain's overall tensile strength is only as good as the weakest link's tensile strength. If the weakest link fails, the entire chain breaks up. When it comes to IoT and OT, OT being the operational technologies area where you typically find IoT device deployments in many industries and organizations. So when it comes to IT and OT, we find that in OT is where you'll typically also find many of these weakness points in security. IT. So over the last several decades has seen an increase in consideration from companies and therefore intensified focus, budget, and effort to protect and defend information technology systems and data. OT, on the other hand, has not enjoyed the same level of investment and attention, and unfortunately, as a result, remains an area of many known weaknesses, as you can see here. That is why attackers are targeting these OT environments. In fact, attackers are hoping that by defeating and compromising OT, and in particular the IoT network-connected devices and systems, they can gain a back entrance to the IT environment of an organization and carry out their attacks involving ransomware and other nefarious activities designed to breach defenses and compromise data and interfere with critical operations. Therefore, protecting these OT systems becomes a priority for defenders. And much of that priority is now focused on protecting IoT and the smart wirelessly connected devices in particular. And if that wasn't sufficient motive for organizations to better defend the OT environment and IoT devices within them, global legislation is certainly coming to essentially force the issue, and we'll touch on that angle later in the presentation. When it comes to defending IoT devices, it's important to note that many of the productive and effective attacks are not just against the remote network reachable interfaces, but also against the local interfaces and physical characteristics of the device electronics in particular. There's a range of attacks that target hardware specifically, for which many of the existing generation of IoT device components are completely vulnerable to and exposed. For example, the so-called non-invasive side channel attacks that target a device's software implemented cryptographic engines, potentially exposing encryption keys used by the device to protect private data and authentication credentials. There are other concerning types of local attacks that can subvert firmware update mechanisms, allowing an attacker to install malicious code directly on the device in the form of a conventional software update. There are also attacks that exploit common weaknesses in debugging mechanisms, typically built into many products that are designed to more easily enable diagnostics, troubleshooting for product support purposes. Those same mechanisms can be used by attackers to compromise and in many cases completely circumvent the device's security controls. Given all these examples, it's important for IoT application and system designers to pay particular attention to those local attack vectors as much as they consider the remote abuse cases and vectors as well. Coming back to the previous point on regulations, it's important to consider the regulatory requirements that are increasingly becoming important in the IoT and OT space. This is very much an emerging area for many of the regulators and standard-setting organizations like NIST and the ISO, and they are approaching the issue from many different directions. In most cases, the standards and regulators are referring to what they often like to define as reasonable security measures. If you look at a typical set of guidelines for OT and IoT environments, what you find is a common collection of concerns. And you see some of them here, directives such as devices should have trusted unique identification. As far as reasonable security goes, this sounds really reasonable. Otherwise, how can an IoT application designer drive authentication and access control without anchoring it on a reliable, unique identity? Another example of reasonable security is data protection. Data definitely should be protected, preferably encrypted on the network as well as when it's persisting on the device's memory. That definitely sounds like a reasonable thing to do from a security perspective, and it sounds like a great idea from a privacy perspective. There should be security and trust and a trusted way to update the device's firmware to make sure that a malicious attacker can't introduce malware or vulnerabilities into the device and the system. That too sounds pretty reasonable. There should be a way for operators, specifically in IT and OT operational teams, to be able to effectively include IoT devices in their security and threat monitoring infrastructures so that these devices can be monitored 24/7. These in turn translate into requirements such as event logging, network and threat visibility in OT and IoT environments. All very reasonable stuff, and if you think about it, what these emerging regulations are trying to mandate is actually based on known and very well tried and tested common sense guidelines that we already have and should have in our IT environments. If they work reasonably well in the IT environment, they ought to work reasonably well in the OT space and the OT operational environment, again, with the right set of capabilities that are appropriate there. When it comes to regulations defined in the EU, requirements are not going to be materially different. It's very common to see the regulators looking for device manufacturers to assume the responsibility of protecting devices and systems and producing devices and systems that have reasonable security measures built in and ensure that they can support the management and monitoring of those devices in an OT and also consumer type environments, including home automation and medical. There is perhaps more pronounced emphasis here on privacy, since the EU is known for its consequential GDPR regulation. Therefore, it's expected that we'll see plenty of congruence between the requirements of standards defined by ITSI, for example, and those we see in NIST and more internationally with the ISO. When it comes to IoT security, everything is built on the proven foundations of cryptography, and those foundations are used by designers and implementers to build solutions that address the 4 key goals of system security. And those should look very familiar to most security professionals, known as confidentiality, integrity, authenticity, and non-repudiation. When it comes to designing and implementing core IoT secure architectures, we consider capabilities such as cryptographic engines with acceleration implemented in silicon hardware and with specific built-in countermeasures designed to resist side-channel attacks. We consider the implementation of authenticity as those employing unique device identities that are rooted in the silicon hardware. This often takes the form of immutable device IDs, and we'll talk about that in more detail in a minute. We look to enforce integrity and non-repudiation using Secure Boot, which verifies public key digital signatures and secure hash-based checksums on firmware loaded into the device's memory at boot time. all the way to employing chip-level sensors and anti-tampering countermeasures that prevent an attacker from being able to defeat any of these security mechanisms by trying to electrically glitch the integrated circuit chip technologies using external means, or by tampering with the debug port's locking and access controls. Fundamentally, we believe that any reasonable implementation of security has to be grounded on the concept of a trusted, unclonable, and immutable device identity. Implementers can't hope to have any kind of reasonable security without this concept and without having access to this type of capability. Just like with airport security, for example, airport security is based on the premise that people are identifiable based on who they are, birth certificates, and even biometrics with fingerprints, for example. And that gives governments the ability to then issue authentication documents that people can carry with them, like passports and visas. That allows people to travel or access different kinds of services and benefits. We couldn't live as a modern society without these concepts applied to individuals. Devices, IoT devices, are very much like that. You need a silicon fingerprint, something very strong and intrinsically deeply rooted in the hardware, unclonable and immutable, and inseparable from the device to then build on top of and enable organizations to securely certify devices, issue authentication certificates, which can be leveraged by application designers to work with different access control policies and permit devices to access certain operations and data, or perhaps not be able to access those things, all depending on the specific policies set by the organization or the designers. Okay, so provisioning and managing such trusted device identities requires secure and trusted manufacturing capabilities. This is really important for device makers to manage, as the chain of trust for device identities and certificates is only as strong as the supply chain risk management implemented by the manufacturers. This is why semiconductor manufacturers are uniquely positioned in the fact that they birth the silicon IC devices in the foundry and are in fact the first in the chain of custody of the device to be able to strongly couple the silicon die to a trusted device identity certificate that can later be consumed by application designers. This year, Silicon Labs introduced the Series 2 IoT product line, which features the next generation of tight integration between wireless connected MCUs and the type of state-of-the-art security features, combining on-chip dedicated security hardware and software capabilities that I've covered in this presentation. Secure Vault, which we formally launched earlier this year, has many of the features you see here and is one of the first wirelessly integrated circuit IoT products to have attained both the IOXT Alliance certification and ARM's PSA Level 2 certification. And I'm incredibly proud of our team for also being recognized with the LEAP 2020 award that was announced just last week. Again, recognizing Secure Vault for its unique, groundbreaking innovation and security capabilities that allow our customers to design and build the best and most secure IoT solutions on the market today. Thank you.